Okay, the next speaker is Balazs Barany, also from Budapest University of Technology and Economics, and he will speak on typical absolute continuity in one parameter families of dynamically defined measures.
Thank you very much. And first of all, I would like to thank the organizers for the invitation. It's always a great pleasure to come back to Poland, and especially to Będlewo in a wonderful place. I really love to be here. And I need to apologize at the beginning of the talk, actually apologize 2 times. First, I would like to apologize from people who has already heard this talk, but in the world of pandemic Zoom meetings and seminars, I think it's hard to avoid. On the other hand, I have to apologize because of maybe not only from you, but the whole math community, because I had a nice paper, nice and short paper from 2014, which was something about related thing. And eventually it contains a little error. But of course, this little error is crucial, so the whole paper is rubbish. I even can point where the error is. So, but after 4 more authors and 4 more pages, 4 times more pages, the result could be saved. So basically, whatever I will tell to you now is a joint work with Károly Simon, Boris Solomyak, and Śpiewak. And what do we want to study here now? So Károly has already talked about self-similar systems. So we will talk about a little bit more general things, which are self-conformal systems, but we will be on the real line always. So we have a finite family of contracting functions. All of them are conformalities, nice, smooth C1 plus alpha maps, and all of them are contracting on R. And then it's well known that there is this one unique, nice, non-empty compact set, which is invariant with respect to these functions, this IFS, in this way. If you would like to understand the structure of this guy, we like to understand it via a symbolic space. So I have m many functions, so I have m many symbols, and from that I produce all possible one-sided infinite sequences. And of course, it's a very nice space. On this space, I have the left shift operator, and from this space, I can project. So I can associate each infinite sequences with one point on my attractor in a very, very natural way. Namely, I take this limit of omega1, omega2 up to omega n with this desired order of this infinite sequence in omega. Of course, this limit is independent of whatever I write here, so I could have written here anything which I like. So it's a very natural projection. It's even called natural projection. And in order to, one way to produce measures on this self-conformal set is projecting the measures from this symbolic space. So in this omega, you have one nice, let's say, ergodic left shift invariant probability measure, and you use this natural projection and push forward it to the attractor to have a nice probability measure there. And you might have several questions about that. You can have geometric questions about the properties of this push forward measure. You can have measure theoretic questions about that, and sometimes you can have geometric measure theoretic questions about that, like what can we say about its Hausdorff dimension, or when is this measure absolutely continuous with respect to the Lebesgue. Okay, and again, just for short, I'm not even sure that this notation will be used, but if you have only a finite word, a finite sequence of symbols from 1 to m, I will denote f of omega as a function to be the composition of the symbols from omega in the correct order. Okay, so what do we know about such kind of systems? Well, there is one nice case which is very nice and very understood when you have separation. What do I mean by separation? So you have your attractor lambda, which is invariant with respect to your IFS. And if the images of that guy are disjoint with respect to two different functions, so I and j are not the same here, and then you know that the images are disjoint, then you can compute all the nice properties about that, like the box and Hausdorff dimension, which is in this case is the root of the pressure, topological pressure defined in such a way. We have already seen it in Károly's talk, but then the functions there were only linearities. So instead of having one pressure, you had there one nice equality. And also, if you push forward your ergodic measure from the symbolic space, then its Hausdorff dimension, upper and lower, doesn't matter, even the Pucking dimension, will be nothing else than the entropy of mu over the Lyapunov exponent of mu, where the Lyapunov exponent is the integral of this geometric potential function. And because of this, I like my Lyapunov exponents to be positive, just like my entropy. Okay, but so this is the case if you have separation. But if you don't have separation, then mostly you have only upper bound, like the box counting dimension, or if you don't know, the Hausdorff dimension is at most the minimum of 1 and the root of the pressure, which is, well, can be called conformality dimension, or the push forward, sorry, this is supposed to be nu, this is supposed to be mu instead of nu. So, and the push forward of your measure has dimension at most the entropy of a Lyapunov exponent. And of course, since in the case of general case, when you can have overlaps, these quantities can be strictly greater than 1. So you need to also take the minimum with 1 of these entropy over Lyapunov exponent and the root of the pressure. Okay, so, but can we say something clever if we have overlaps? Let's say at least typically in some well-chosen sense, do we have equalities here? Just like in the case of non-overlapping situation. Yes, non-overlapping situation. Well, in the special case, which we have heard in the previous talk, when all the functions are similarities, so not only conformal maps, but everything is similarities, we have very recent, well, maybe not so very anymore, but still recent results on that. So for example, Polikot and Simon in 95 calculated when in this paper they introduced the so-called transversality method, and I will talk about this later, a kind of solution for the 0-1-3 problem. And there they showed that, well, if you choose your lambda value to be typical from this interval, below and after that it's not so interesting, but on this interval, then you can calculate the dimension of the measure, which is equal to the conformality dimension, almost surely. And then in 24, Hochmann came and introduced the super exponential separation condition, which is even weaker than what we have seen in the weak separation. This says basically that, for example, in the case of 0-1-3 problem, that if this super exponential separation holds, then again, the dimension of your set will be the equal to the root of the pressure, which is the similarity dimension, as it was called in the previous talk. And any Bernoulli measures dimension equals to the minimum of 1 and the entropy over Lyapunov exponent. And in the case of, let's say, the 0-1-3 problem, it says that the super exponential separation holds outside of a 0 Pucking dimension of set of parameters. So it's a much better estimate on the exceptional parameters where it doesn't hold than it was known previously. So this is what the Hochmann implies, but his method was relying only to have Bernoulli measures. So from the symbolic space, you were allowed to push forward only Bernoulli measures, which were which are the self-similar measures, but this was extended by Jordan and Rappaport for ergodic measures. And also they are saying typical in this dimension sense. So if you have a one parameter family of iterated function systems like here, and your parameterization is smooth enough, let's say everywhere it's analytic, then outside of a zero-dimensional set of exceptional parameters, you know what is the dimension. It's entropy over Lyapunov exponent. But were you also, for this special case of Bernoulli convolutions, can say that also if you know that lambda is transcendental, then you can be sure that the dimension equals to the 1, regardless of what. So in the case, and also, so this is about the dimension, and the case of absolute continuity, thanks due to the work of Schmerkin, in again, for example, for the case of Bernoulli convolution, we know that except a zero Hausdorff dimensional set of parameters, this Bernoulli measure, the uniform Bernoulli measure, where the weights will be 1/2, 1/2, so the uniform Bernoulli measures push forward, will be absolute continuous, or you calculated it for some algebraic case. And then later, Schmerkin and Solomyak for uniform contracting ratios, then Sagliette, Schmerkin, and Solomyak for general contracting ratios, but all of them for Bernoulli, and they were giving conditions like parameterized family, and you know that for Lebesgue almost every, and the exceptional set has dimension, at most this and that. So these kind of results. But these strong results are heavily relying on kind of very strong additive structure of these self-similar systems. But if you have conformal system, then you lose this kind of nice algebraic structure immediately. And still, the only and best thing what you can work with so far, according to my knowledge, is the transversality method. So for example, on the line, if you have a parameterized family of conformal iterated function systems, then Simon, Solomyak, and Urbansky calculated the dimension again, which is the entropy over Lyapunov exponent for almost every parameters. Later, Perez and Schlag gave estimates for the exceptional sets. And well, where this kind of exponential, super exponential separation condition works, there is some which are the rational maps. This is due to Hochmann and Solomyak, but the advantage of the rational maps is that they somehow still have nice algebraic structure in the system. So since later on I would like to use this transversality method, let me state precisely the theorem of Simon, Solomyak, and Urbansky in our situation. So you have a bounded open domain of parameters, and you have a parameterized family of conformal iterated function systems on the real line, such that it has two properties. One property is that we assume that this system in the parameters is uniformly hyperbolic, namely you are uniformly separated away from 0 and 1. And also you depend quite nicely on your parameter, namely this is just a nice continuous way. And also the transversality condition, which is the second one, holds. But what does this mean? So when can we handle the situation? We can handle the situation if there are no overlaps. That makes us happy. So maybe in the case, if there are a few and very little chance for overlap, then we can still handle it. And this is what it says, because if there are overlaps between two different images of the attractor, then there are two guys who already begins with different symbols, but their natural projection coincide. So what I claim is that there should be some uniform constant such that if I meet with two such kind of infinite sequences where they should not be the same, so their first symbol all immediately different, and unfortunately the set of parameters where they are close to each other, so the distance is at most r. Of course, on symbolically they shouldn't be close, but the set of parameters where they are actually close on the attractor is small. So this measure of parameters is bounded by the measure of the distance, so constant times r. And if you have this, that there's a little amount of parameters as possible, that these two guys are close to each other, then whatever fixed ergodic measure you have on the symbolic space, and you push it forward down to the attractor, then there will, for Lebesgue almost every lambda, the dimension will be nothing else than the entropy over Lyapunov exponent, and this measure will be absolute continuous with respect to the Lebesgue whenever this entropy over Lyapunov exponent is strictly greater than 1, again still for almost every lambda. And a natural kind of such parameterization is if you fix your functions f1, f2, fm, and so on, and your parameters would be just, translation parameters. In order to satisfy this condition here, what you need is that the derivatives, the subnorm of the derivatives of these functions is at most 1. Okay. But why is it interested to be fixed? Because of course, the set of Lebesgue positive set here will depend on measure mu. A priori, it can depend on measure. But in this talk, we really would like to study such kind of measures on the symbolic space, so such kind of mu measures which are depending also on the parameter lambda. So now you can ask that why? Why do you want to harm yourself with such kind of things? Well, on one hand, in my opinion, because it's fun, but actually there are natural examples where such kind of measures appear if you have a parameterized family of iterated function systems. For example, one thing is the dimension maximizing measure or the equilibrium measure with respect to my nice potential function, which comes from the geometry. So under the assumptions of Simon, Solomyak, and Urbansky, what we have is that the dimension for my parameterized IFS, then of course the attractor will depend also on the parameter, will be almost surely the root of the pressure, but the root will also depend on. But they don't know whether there is a dimension maximizing measure. Because why? What is the dimension maximizing measure? Well, if I take this potential, which is a nice Hölder continuous potential in this case, because my functions f are c1 plus alpha, this is a nice uniformly Hölder continuous potential on my symbolic space, then of course this will depend on my parameter lambda. But I also know by Bowen that there exists a unique ergodic shift invariant measure, which satisfies a kind of variational principle. So the mu measure of any finite word with respect to this mu lambda will be comparable with the diameter on of the attractor, which of the points which begins with omega 1 omega n. So basically, this measure will immediately depend on lambda. And the other good thing is that the entropy over Lyapunov exponent quantity of this guy will be the conformality dimension. That's one natural thing. So if you wanted to know that there is a dimension maximizing measure, then you need to project this guy and verify whether its dimension equals to that. Or the other one, which I used to call place-dependent cell-conformal measures, which are coming from the chaos game. What's the chaos game? So the chaos game is some nice little Markov chain on self-conformal sets. So the standard chaos game says the following. Take a probability vector P1, Pm, and, well, take a coin with m sides, such that it lands on the side I exactly with probability Pi. Okay, you toss a coin, you are somewhere on the attractor, you are standing on the attractor at point X, toss a coin, it lands to Pi, it lands on I with probability Pi. but then you step to f of I of x. Okay, and it's a nice, well-defined Markov chain on my self-conformal set. And then the stationary measure of this Markov chain will be exactly the self-conformal measure, what we have seen in the previous talk by Károly. But of course, if you say that your probability vector depends on the point, then you won't ruin the Markov property, right? So instead, we say that there is some pi I function, nice Hölder continuous function on lambda, such that they sums up to 1, right? But it depends on the point. And if you are standing at the point x naught, you toss your coin, which is depending on your position, which depending on your place, it lands on side I with probability pi I of x naught, and then you step to fi of x naught, right? It's still a nice Markov chain on your attractor, on your self-conformal set. And for example, by the result of Fan and Lau, the stationary measure of this Markov chain will satisfy this nice equality, right? Exactly, this is the stationarity. And of course, this measure, if you now have a parameterized family of iterated function system, this will also depend on the parameter. Why? Because actually this new measure, the stationary measure here, is nothing else than a push forward of another Gibbs measure, of another nice equilibrium measure with respect to this potential function, right? And since if your IFS depends on some parameter, then the natural projection also depends on some parameter. Hence, this measure will also depend on some parameter. So if you want to say something about such kind of measures, then you must also consider parameter dependence on the measure. But in order to say something, you need some extra stronger regularity assumptions. Because usually what we assume is that my IFS contains C1 plus alpha maps. Now it's unfortunately not enough for us. We need to say that these maps of the IFS are more regular. So they are depending on the parameters in a C2, sorry, they are a C2 plus alpha dependence. And also the dependence on the parameters shall be also more regular. So instead of just saying that they are depending continuously on the parameter, they must depend in C1 plus alpha V on the parameter. And also some on the partial derivatives, we also need some kind of nice bounds on the Hölder continuity. And there is unfortunately one technical but important thing. So instead of looking at bounded domains of our parameters in RD, we must have, and actually, okay, we mustn't have, but we have to have here one-dimensional parameter family. So we have only a one-dimensional parameter family instead of the previous high-dimensional parameter families. Of course, it restricts somewhat. But of course, what is the other thing what we want? What we want is the assumptions coming from Simon, Solomyak, and Urbansky. This means the uniform hyperbolicity and the transversality condition. This is somewhat different what I stated there, because there it was formalized with the measures, right? So, but in this kind of under this kind of smoothness assumptions, this C1, C2 smoothness assumptions, this kind of transversality is exactly the same as we have seen so far. So basically, what does this mean? This means that if you plot the function, the natural projections, P lambda, whoopsie, I did something, P lambda of omega as a function of lambda, and also you plot P lambda of tau, they must intersect in this transversal way. And this holds if and only if the measure of the parameters where they are close to each other is tiny. Okay, these are exactly the same things. Okay, so this is our assumption on the IFS. And of course, as usual, we need some assumptions on the measures as well. So what are these? What is this assumption? Well, the measure must also depend somewhat regularly on your parameters. And what I claim first, a kind of uniform weak star continuity. What do I mean about the uniform weak star continuity? So for every epsilon, regardless what, you can find the delta that if your parameters are delta close to each other, then the tau, mu tau, and mu lambda measure of the same cylinder are also close to 1 in the following sense, that they are close to 1 with error e to the power epsilon times length of this cylinder. Of course, we cannot claim that this won't depend on the length of the cylinder, because if it won't depend, then this would be exactly the same measure essentially. So it must depend on the length, and this is the natural dependence. And also we need to assume another kind of regularity, which is that the entropy depends continuously on the parameter. Unfortunately, this cannot be deduced from here, but we need to assume that, so we assume it. And in this case, what we have shown that for Lebesgue almost every lambda from my parameter family, the Hausdorff dimension of the push forward of my parameter dependent measure will be whatever it shall be, 1 and entropy over Lyapunov exponent. And I have to note here that this result in this form essentially was proven by myself and Michal Rams in some other paper, which was about dimension maximizing measure for self-affine. But that was very, very a special case, and this is a more general one. And what about the absolute continuity? Yes? The previous theorem. The previous theorem is, up to this moment, there is no difference. Up to this moment, is stronger assumptions than the Simon, Solomyak, and Urbanski. But what we allow is that the measure here depends also on the parameter on which my IFS is depending on. And this they could, yes, plus transversality, exactly. And also still you have transversality for if you want to show absolute continuity, but you need, and again, more regular dependence for the measure on the parameters. And well, this kind of dependence can be interpreted as, let's say, uniform Hölder weak star continuity. Let's put it in this way. Because instead of the saying that for every epsilon, you can find some delta, that these guys are close to each other, you must know exactly how they are close to each other, and they must be close to each other with an error up to the distance of lambda and tau to the power theta. This is why I'm saying that it's kind of further, and we still need the continuity of the entropy. So then what we have, that under this bunch of assumptions, the push forward of lambda mu will be absolute continuous with respect to the Lebesgue, almost surely in the regime of the parameters, the entropy over Lyapunov exponent is strictly larger than 1. And basically, this theorem is an adaptation, and of course, this was a very hard part, adaptation of the proof of Perez and Schlag, who were proving bounds on the exceptional parameters, where this projection here is not absolutely continuous. So they were giving bounds on the dimension of that set. But of course, this measure then for them was not allowed to depend on the parameter. The price is that we could not adapt the part of the Perez and Schlag paper, which gives you bounds on the exceptional set. Just we know that the exceptional set must have 0 measure. Okay. So, but we have seen these two kinds of example, right? One was this equilibrium measure, the dimension maximizing measure. The other one was the stationary measure of this chaos game Markov chain. And very fortunately, both of them satisfies all these conditions, as I said, if your IFS is regular enough. And why? Because if you have a potential, a general potential on your symbolic space, a Hölder continuous potential, such that not only the potential is Hölder continuous, but the dependence on the parameters is Hölder continuous, then you have a Gibbs measure which satisfies the strongest regularity claim in our paper. And hence, what we can show is that if you have this Gibbs measure, mu lambda, which depends on which is the Gibbs measure with respect to this potential, and your potential is regular enough, then you know for almost every parameter values whether what's the dimension and whether is it absolutely continuous or not. You know it almost surely. And actually, in the first case, if you're looking at the dimension maximizing measure, we can say a little bit more about the regularity of this measure. Namely, if you look at this special potential, right, which you guess that would like to give you the maximal dimension, then on the set of parameters where the conformality dimension, recall that this was the root of the pressure, is strictly greater than 1, is not only absolutely continuous, almost surely, but also absolutely continuous with L2 density function. Okay, so in this case, you have a quite better regularity. Oops. Well, that was also a big disadvantage, that we allowed only one translation parameter, not high dimensional parameters, and not introducing all the functions with one translation. But if you have 3 functions, that this is essentially not a big restriction, because then you can parameterize your system as that you does not perturb your first and third function, but use the translation as one-dimensional parameter for your second function, and you can parameterize it in such a way that the 0-1 interval is still mapped into itself. But furthermore, what you need is that these two guys shall not intersect. I mean, the image of the 0-1 interval, right? Because you only want a transversality where you depend on the parameter. And well, if these two guys meet and they are not depending on the parameter, then you are in trouble. So you must ensure that these two guys are separated and just the middle guy is moving up and down between them. Okay, and of course, there is one natural thing which we need to assume if we want transversality, namely the derivatives at most 1/2. Okay, so for example, this is one thing when all of your machinery works. There are a few other things where it works. For example, the place-dependent Bernoulli measure. And the place-dependent Bernoulli measure can be also viewed as the SBR measure, or the projection of the SBR measure of some nice hyperbolic action with singularities. So take a square, actually not square, rectangle, of sides -1, 1, and here side 0, 1, and take a line and divide it into 2 parts, right? Upper part and lower part. And now your action will be that you will put this guy here in such a way that here you contract uniformly by lambda. And in this direction, you will expand always for each slice as large to end up with a full height. Okay, and you also have to do it with the lower guy. Whoops, that was wrong. Actually, this upper guy goes here. So, okay, but you have some formula for that. And basically, if you are interested in these actions SBR measure, it won't be anything else than the Lebesgue measure times the stationary measure of my already seen Markov chain. The stationary measure of the chaos game where you choose your probabilities according to this rho times x plus 1/2 dependence, right? And if you're interested in whether this SBR measure is absolutely continuous, then you can do this by knowing that whether this new measure, the stationary measure, is absolutely continuous. Okay, and where we end up is this picture, which says that we know that this Bernoulli convolution, which acts in this x direction, where is it transversal? It's transversal on the parameters between 0.5 and 0.66. Below that, you cannot expect absolute continuity. And for every row, if you draw here a line, I try to draw here a line. So for every fixed row, if you draw here a line, you can be sure that on this region, for almost every lambda, you are absolutely continuous on this line. If you are here, then you must be singular for every point. And why did I consider here this linear division instead of any arbitrary Hölder division? The answer is very simple, that with my ad hoc methods, it was possible only to produce this kind of nice picture for that simple system. But of course, the same result works if you replace this nice line with some Hölder and you approximate the entropy a different way. Okay, another thing is where it might be interesting in the also somewhat related to iterated function systems are the hidden Markov chains. And how the hidden Markov chains are related to iterated function system. Well, there is a result of Blackwell, who calculated the entropy of hidden Markov chains on finite state space. And let me present here only a very special case. So namely, you have a Markov chain, which is defined as follows. You have two states, 0 or 1. And if you are at one stage, you switch with probability 1 minus p, but you remain in the same stage with probability p. Okay, this is my Markov chain. This is a nice stationary Markov chain, well understood, no problem. What's the entropy of this? Okay, but now you introduce a new noise. A noise which appears with probability epsilon, and there is no noises coming with probability 1 minus epsilon. And the hidden Markov chain will be this Zi, which will be the sum of the Markov chain, which is the message which comes from you, and the error. And this is what you can observe. This won't be a Markov chain, this will be a hidden Markov chain, but by the result of Blackwell, you can calculate the entropy of it, but this entropy is pretty much disgusting, as you see. I mean, quite disgusting to calculate it, but anyhow, it turns out that in the formula, what you need is to integrate with respect to a place-dependent probability measure, where these are your functions and these are your probabilities. You shouldn't care about this. It's much more interesting to look at this picture, because it will say that if you are looking at the blue region of the epsilon and p parameters, here you are always singular. So in this part, you are always singular, no matter what. And this was shown in this paper of mine with Mark Polikot and Károly Simon. But in the region, in these red regions, actually what we have shown with István Kolozsvári, that the transversality holds there. And again, how does the transversality hold there? So if you draw this line, this vertical line, is vertical. Then wherever this intersects these things, so for every fixed epsilon, if it intersects here, then in this interval, it satisfies the transversality. So using our result, we know that this Blackwell measure, this place-dependent probability measure, which helps you to calculate the entropy of the hidden Markov chain, will be absolutely continuous. We have no idea about the regularity, but will be absolutely continuous. Okay, so that's a second example. And in the remaining, I think, 9 minutes, let me bore you with the sketch of the proof, but only the sketch of the proof with the dimension case. Okay, so what was the dimension case? We needed this kind of uniform weak star continuity, regularity for the measures, as they are depending on the parameter. And also we needed that they are depending continuously, the entropy is depending continuously on the parameter. Okay, what shall we do now? We will pretend now that we have a kind of Egorov theorem for every parameter uniform. How can we do that? Well, a priori we cannot, but we can say that fix your lambda naught, your favorite parameter there, okay? And you are looking at all the infinite sequences such that after this capital N, your cylinder has more or less measure compared to the entropy, comparable to the entropy, up to an error of 2 epsilon. And here you have Lyapunov exponent at this lambda naught, again with the error of 2 epsilon, for every n who is very, very large, larger than this capital N. And what I claim is that because of this continuity assumption, if I choose the neighborhood of lambda naught very, very tiny, like such that the distance between mu lambda, so if I choose that mu lambda minus h mu lambda naught is at most epsilon for every lambda in V, then this guy, this union for all capital N still will have full measure for any lambda here, right? So what we will do is just, instead of looking at my original mu lambda measure, we will restrict ourselves to one of these sets for very, very large n. But still, this inequality will hold, very fortunately for them as well. Okay. So now, how can we show that the dimension of a measure is at least something? Because the upper bound is already known. The upper bound holds without anything, without dependence on parameters, without not dependence, it holds always. So we want a lower bound, and we want to show that no matter what, this will be a lower bound for my dimension of the measure. Okay? And one use for that is the Frostman lambda. So what we want is that this energy integral of mu lambda is finite. Then we will be completely sure, even we know more, but we can be sure that the Hausdorff dimension is at least alpha. And how can we ensure that for a typical parameter lambda? Well, if you integrate it with respect to lambda and it's finite, then you won. Okay. And what is the standard trick here? The standard trick, like in the Simon, Solomyak, and Urbansky, they didn't have parameter dependence. So what did you do? Apply Fubini, exchange the two integrals, and whatever you see inside will be finite by the transversality assumption. But what's the problem? Our trick is immediately killed, since this guy depends on the parameter. So of course, you want to get rid with this dependence of the parameter. How can you get rid with this dependence? Well, first, you just rewrite this integral with this sum. Of course, there's not inequality, but up to a uniform constant, these two guys are the same. And now you want to try to get rid here. And first, you use how nicely your IFS depends on the parameter. Because if you choose Q sufficiently large, then you don't really need to care what this omega is. What's the infinite sequence of omega? It's absolutely enough for you to care about the first Q times n elements. Because whatever is after that, it doesn't matter. They are already very, very close to each other. And up to some price of here on the distance, which is a uniform constant price, you can say that this sum is replaceable with this guy. But what is this guy? This guy is just a sum of cylinder sets of measures. And what do we have? We have exactly assumption from them, how it's changed. And how will it be changed? Well, if the diameter of V will be pretty small, then it will be more or less the length of the cylinder, which is Q times N times epsilon. So this error term jumps here. And now you are in a good position because instead of lambda, you have here lambda naught. And now this guy doesn't depend anymore on the parameter. You immediately apply Fubini and everything goes as it should. So that's basically the sketch for the dimension. But the sketch for the measure is more difficult because you want to apply some similar trick there. So again, the Simon-Solomyak-Urbansky word as follows, that you were looking at the lower density function of your measure, and you wanted that it's almost surely finite. And if you integrate it with respect to the parameter, you know that for almost every parameter it's finite. So what you wanted is that, again, apply Fubini, exchange lambda, right? And how did we get rid with this not possible? Well, how did we get rid with the fact that for us, this Fubini doesn't work because the measure depends on my lambda parameter? Well, we approximated the lambda with some lambda naught, right? We wanted this approximation from jump here to lambda naught and then exchange and hope the best. But then, exactly by the same reason why this epsilon error term jumped in, an extra epsilon error, depending on the size of the ball, will jump in here. And then this guy, if you divide by R, won't go to 0. So you need something more powerful technique, which is adapted by Berns and Schlag, and they were considering Sobolev spaces, Sobolev energy. And basically what we have shown that the Sobolev dimension of these measures are greater than 1, because in this case, what you have here, if the Sobolev dimension is greater, then your Fourier transform of your measure is in R2. And that will be completely enough. But I don't want to go into the details, especially since everybody and I'm hungry. So I would like to thank you for your attention.
Thank you for a great talk. Are there any questions from the audience? From online? Okay, if not, that thanks the speaker again. And before the lunch and the photo, I would like you to give me 3 minutes for an announcement, okay? And the announcement will consist of 3 slides, which I would like to show you. So please give us half a minute to prepare. But I think stop.